Welcome to this section on galaxy formation and evolution. I've been tasked to give you a review of this entire field, and I have 20 minutes, so I'm not going to do justice to everything. So it will be a quick whistle tour stop, but my focus is to just give you a sense of what are the big ideas we're working on at the moment and how it connects with all the things all of you might be working on at the moment. Because I think if the situation we're in at the moment is that we're realizing that galaxy formation and evolution is a huge multi-scale, multi-process adventure. And that comes as no surprise, probably. We need to deal with the formation of stars, and we need to deal with how galaxies are embedded in the cosmic web. But what's really, really changing is the realization that we need to look at all these things in synergy, because they all rely on each other. So we can't anymore slice this problem and look at one thing at a time. We really need this full, holistic picture. Now, I realize this is a broad audience. Some of you probably don't think about galaxies very often. So I've put on the slide some more technical details for the experts in the room so they have something to satisfy themselves. If you're not an expert, just hold on to what I'm saying. I'll try to keep that at a level where everybody can follow me along. All right, we'll just start with a very brief overview of the ideas over the past 50 years, just to put in context the ideas that we're currently playing with. So this was introduced yesterday by George. 50, 60 years ago when the IOA started, we were really in a mode where galaxy formation was a top-down approach. Early collapse of gigantic clouds of gas that formed monolithically single galaxies. Then in the early 80s and 90s, with the advent of cold dark matter simulation, things flipped around, and we started having a more bottom-up model for galaxy formation, where the focus was hugely on the merging of smaller structures into larger and larger structures. This was fueled by these simulations based on the cold dark matter framework, and at the same time, as Richard just mentioned, we had HST that started to give us first images and detailed physical information about these high redshift galaxies. And by looking at those, they turned out to be all very highly star-forming galaxies with very disturbed morphology. Now, by analogy to galaxies in the local universe, these very highly star-forming galaxies are all major mergers. So that, again, gave evidence in favor of this thing that really merger was really the thing driving galaxy evolution. But slowly, we started to see cracks in this picture, including the fact that these high redshift galaxies that look just very clumpy blobs in these HST images, if you look at their kinematics, they turn out to be beautifully ordered rotating disks, just like your normal spiral galaxies in the local universe. Now, it's very difficult to explain how you can have a major merger, yet preserve this beautiful rotation. At the same time, with new instrumentation, we're able to look at the gas contents of these galaxies at high redshift, and we found out that they were very, very gas rich. So based on all of this, a much more natural explanation emerges to see that, well, these high redshift galaxies, they're no different than our local galaxies in many respects. They just happen to be very more gas rich, therefore they produce a lot more stars. At that same time, we have development of theoretical and computational work that really reinforces that picture that this galaxy evolution is very much gas-driven. So there's the emergence of a set of very simple analytic models that represent galaxies as very, essentially as a simple mass conservation equation. All the gas that comes in either needs to be transformed into stars via star formation. It either settles into the gas reservoir or is ejected right back out of the galaxy. And this very, very simple and what might look quite naive model is extremely successful at reproducing a lot of our observations, and I'll show you some of that later. At the same time, we have huge suites of hydro simulations that really emphasize that it's just not the merging of little blobs of dark matter, it's about the flows of gas in and out of these galaxies. So all of that puts us in this modern picture where we're thinking of galaxies as these sort of living, breathing objects that feed with these gas flows, transform some of that material into stars, and then return some of that material to the outside environment. And in our jargon, we tend to call that the baryon cycle. Now, why did we, okay, lots of things, I don't expect you to read all of this, but just to give you a flavor of why we ended up there. And a lot of that ended up being because in the early 2000s, there was a burst of new technology for sort of millimeter, submillimeter, and radio telescope that allowed us for the first time to not just look at the stars in galaxies, distant galaxies, but also look at their cold interstellar medium. By being able to assemble large samples of galaxies with information not just about the stars, but the gas, we can really put this whole picture together. So once we have this, right, for all my galaxies, I know not just about the stars, but I know something about their interstellar medium. I can start asking questions about, for example, what sets the star formation activity of galaxies? Because, if we put it simply, if we could know exactly why galaxies form stars or not, in what environments, under what conditions, at any point in time, well, then that's pretty much job done, right? We can really understand why different galaxies grow in different bits of the cosmic web and so on. So we really want to understand this question: why do galaxies form stars or not? So when we do this, we often look at this quantity, specific star formation rate. So how much star formation rate per unit mass does your galaxy have? And now I'm just going to multiply that by factors of 1, but carefully chosen factor of 1s, because those put into play different components of the gas reservoir. So we have the observation. We can look separately at the H1, which, if you look at this image, that's the very diffuse bulk, large-scale gas reservoir. A lot of it has nothing to do with star formation just yet, but it's sitting there and it has potential to eventually flow in and trigger star formation. Then we have the molecular gas, so that tells us how much of the gas is actually in regions that are dense enough to form stars. And finally, we need to consider the star formation efficiency. Once you have your molecular clouds, how efficiently do you convert that gas into stars? And with these large surveys that I just mentioned, we can canvas, broad representative parameter space and have a look at how all these three quantities vary across the galaxy population. And what we're finding, so there's sort of a good mapping between these three things down here and these three panels. Again, details don't really matter, but what you should notice is that there's systematic gradients in all these three panels. So if you want to understand how the star formation proceeds, why we get a certain amount of star formation, we really cannot ignore any of these three things because they all vary in different directions, and it's the balance of the three together that produce this bimodality of the galaxy population, and so on. So that tells us that the star formation output of a galaxy depends on all these three things. How much fuel it has, which I measure with this H1, and that tells me something about the connection of galaxies with their very large-scale environment, because that's how you get gas, that's how you resupply these large-scale gas reservoirs. We also need to understand how you form molecular gas. It's not enough to have these extended gas reservoirs. You need to cool some of it, bring it to dense enough regions where they have the potential to form stars. But that's not the end of the story. What we're finding is that the efficiency of the conversion of the molecular gas into stars is also something that varies systematically across the galaxy population. And that's down to very small scale physics in the galaxies. Now, my idea for this talk was that I was going to give you an overview of all these three things, and then I realized in 20 minutes that's just impossible. Thankfully, looking at the program, a lot of this is covered in later talks, so I'm just going to focus on this earlier part and mostly talk about the connection between galaxies and their large-scale environments, looking at these gas processes. All right. Now, so we want to study the supply of gas into galaxies. That's, step one in this process of galaxy growth via star formation. We could try to go and look for these gas flows directly, but that to this day remains an extremely challenging process. We have, some very, very limited evidence. So what I'm going to focus on is a slightly more indirect approach, but one that still has a lot of potential, which is to look at the material that is embedded within the galaxies already. So by that I mean the interstellar medium as well as the stellar populations, and see what information we can extract about these larger scale flows of gas from what's in there and what we can measure quite robustly. So again, the details don't matter too much, but with very, very extensive efforts over the past 2 decades, we now have this sort of network of what we call galaxy scaling relations that correlate all sorts of properties from star formation rate to the amount of gas, kinematics, sizes, and so on, with mass or various properties of galaxies. So we've done this well for galaxies over quite a broad range of masses and up to redshifts of easily 3. And now with JWST, we're breaking into the much more distant universe. Now, each of these relations individually is not particularly interesting, but what matters is that they all have different inflection points, they all have different evolution with redshift. So it's in the connection between these relations as well as the scatter of galaxies about each of these relations that all the physical information is. So I just want to give you an example of how we can use that information. So I told you earlier we were in this global picture where galaxy evolution is driven by gas flows in and out. We call this the equilibrium model. Because based on this naive idea, you expect, for example, if you have a galaxy and it just accretes a bit more gas, so there's fresh gas flowing in, so that will have the effect of triggering some star formation because you have more gas. And that triggers more feedback, so you return more gas out, and then the galaxy falls back to its equilibrium. Now, by putting more gas in, what you're doing as well is diluting the interstellar medium. So the chemical enrichment of your interstellar medium should go down as well. So the theory expectation is that galaxies should oscillate between periods where they are gas-rich and low in metals because they've just accreted fresh gas. And then they work themselves back towards a point of equilibrium. And then it might go the other way around. So they have periods where for a brief period, they're gas depleted, but they're particularly metal rich. And again, and this is from simulation, so you have the benefit of knowing the time evolution, so you can see this kind of restoring force that wants to bring galaxies back to their point of equilibrium. So that's the theory expectation from simulations, but that was just one mass spin. Now, if we start looking in galaxies with progressively more masses, we can see that while simulations and theory match very well at these low masses, things completely break down in more massive galaxies. And that's because here we start having a lot more different physics at play, including, for example, feedback from supermassive black holes. That mean that galaxies no longer have this restoring force that works to keep them in their state of equilibrium. Now, we wanted to see if we can see all of that in observations as well, and it turns out we can. So again, just look at this top panel. Again, it shows you the deviation in metallicity and gas content. So this is for low mass galaxies where the data goes well with these simple equilibrium models. And then we go to higher mass galaxies. As we had in the simulation before, this thing flips over, and really we can't, the equilibrium models simply don't do the job anymore. So if we look at all of that in one go, so that's down here. So we've got the observations as the points and the pinkish thing. We have different suites of hydro simulations, and we have this theoretical equilibrium model as the line. Now, at low masses, everybody pretty much agrees. We all see this kind of equilibrium model at play. At high masses, it's all over the place. The different simulations don't agree with each other. The model, the theory, and the observations don't anymore. So our beautiful equilibrium model that works so well for many galaxies and it produced many observations, we're starting to see cracks in this, and it manifests itself, for example, in these high mass galaxies. Now, what this tells us as well is that these observations of not just the stellar content of galaxies, but their gas and their chemical composition is hugely constraining for simulations. Right? So if you're trying to understand which feedback prescription, for example, is best suited in your simulations, there's a lot of useful information from these observations beyond just looking at their stellar contents. All right, let me give you a few more examples of what we can do in this kind of field of research. And because it was introduced in so much detail yesterday, I'm going to show you what we can do with DESI not for cosmology, which is what it was designed for, but if you try to scavenge all those 40 million spectra to do a galaxy evolution study. It can do a lot of things. The place where I find a lot of the really, really interesting stuff is coming is from the very, very nearby universe. Because DESI selects galaxies up to magnitudes of 19.5. That's 2 magnitudes fainter than SDSS. So you can really, really go down. So if you think about the full mass range of galaxies, with SDSS, you really only start from about 10 to the 9, so pretty massive galaxies. So with DESI, we can add full 3 orders of magnitude in mass to our studies. So the challenge is, how do you extract all the physical and chemical properties of the galaxies from these spectra, which are relatively shallow because they're designed to get redshift for cosmology. Again, I'll skip the details, but you can do it if you're very careful. And then you can do something like this. So this is the so-called mass metallicity relation. This is the metal abundance in the gas phase in these galaxies as a function of mass. So previously, as I said, this thing was well calibrated down to about 10 to the 9, and with DESI, we add these 3 orders of magnitude and stellar mass. And it looks like just a beautiful extension of this, and you think you'd be happy. But this is really doing things business as usual. You just take whatever galaxies you detect in your survey and you put them on the plot. The beauty of something like these large surveys is that you can have very mass complete representative sample of the full galaxy population. And when you do that, this is what the mass metallicity turns into. So we see a huge departure from this linear regime in the low masses. So when you look at really the full picture, there's an inflection point here at about 10 to the 9 where galaxies, they don't go quite metal poor as it seems like they would. Now, what's interesting is to start comparing with the new results that are coming in from JWST at very high redshifts, where, this is a very, very active field. There's still no consensus on what the results are, but there's starting to emerge results where in this similar mass regime at redshifts greater than 3, you also have this sort of shallower slope emerging, which has always been here in the local universe as well. We just really weren't sensitive enough to pick that up before. Now, how do you explain this change of slope? It can have something to do with how the feedback works and how you couple the energy from, for example, supernovae to the interstellar medium. All right. So what can we do with DESI? So I don't have time to go into all of this, but this changes the question, right? So we've sort of uncovered this new inflection point in galaxy scaling relations at this kind of 10 to the 9, this entry into the dwarf galaxy regime. We see, I haven't time to show you, but we've discovered when you look at the gas, we see that there is a similar inflection point. So there's clearly something happening in these galaxies at that mass scale. It could have to do with a change in how they accrete gas. It could have to do with a change in how the feedback is able to drive material back out of the galaxies. But at least with these very large surveys and looking at this combination of probes that look not just at the stars, but at these other components, now we have a much better refined set of questions that we can explore with all sorts of things. And again, these are the kinds of things we can do with DESI that my team is working on. So if anybody cares about these things, we can talk about that later. But just to start concluding, so whereas it might have looked like we were starting to get things figured out, I think the field has really exploded in the past few years, and we have a huge set of questions that we need to answer. I've only started touching today a bit on these things on the left, which has to do with the gas supply and how you feed galaxies, because that's step one if you want to have star formation and galaxy growth. I haven't even touched on these questions about the star formation efficiency, but that's another fascinating area of research, which we should hear about from Eva later this morning. So how do we do this? How do we make progress? Well, I think we need to, again, take this very holistic picture and say we need to look at all of this at once, and we need to use what the universe is giving us. And different components of this baryon cycle are better studied in different galaxies at different cosmic epochs. So we can use this natural change in galaxies that are sort of in the local universe where you have very little gas accretion. So you know evolution must be dominated by more internal processes compared to these very, very high redshift galaxies that are very energetically fed with gas constantly. So that's it. So I think we're at the point where, we heard yesterday, to do precision cosmology, we can no longer ignore the astrophysics. And at the same time, from our side as well, because we have a broad range of tools, we can get this much clearer picture. But to do this, we need to have these very large surveys that are systematic, that cover broad parameter space, and that do this using a full range of tracers. And yeah, I think I'll leave it at that. Thank you.